Now let's do another example. Here it asks to find the points on the cardioid where the tangent line is horizontal and vertical. Remember, the tangent line is vertical when dy by dx is infinity, and it is horizontal when dy by dx is equal to 0. And I did these types of questions also in the previous sections for the parametric representations. So I'm not going into all these derivative relationships in detail. Okay, so if you need some more assistance, please go back and refer to those videos. Right now, here we know that the representation has this format, so it's just a matter of calculating these two things. And now also, when this is 0, while this is not equal to 0, we'll give the derivative to be equal to 0, and if the denominator is 0, and at the same time if the numerator is not equal to 0, then this will give infinity. But the only problem we have is if we get something like this, and we will see how we are going to deal with the situation like this. Other than that, we can directly obtain the required behavior, right? So we just have to check the points where this becomes 0 and the points where this becomes 0, right? So dy by d theta, that is the numerator, is given by this equation. We obtained this relationship in the previous video, right? And you can see if this is 0, that means if this is 0, then that means either this is equal to 0 or this is equal to 0. And cos theta equal to 0 means theta should be pi by 2 or 3 pi by 2. And now there's another thing that I want to mention. Here we are measuring the angle, like we should fix the direction of measuring the angle. So if we are measuring it in the clockwise direction, we should measure all the angles in the clockwise direction. Otherwise, if we measure one angle in the clockwise direction and if we measure another angle in the anti-clockwise direction, it will like the calculations will not be consistent throughout, right? So, and also if, like, say for example, if theta is equal to pi by 2, that means at this place we will have dy by d theta equals to 0, and we can see that the denominator is not equal to 0 at theta equals to pi by 2. So at pi by 2, that means in this horizontal, the vertical line, that is the y-axis, we have dy by d theta, dy by dx equals to 0, right? And also we can find the value of r at theta equals pi by 2, right? How do we find the value of r? We just have to substitute it in this formula. So r will be equal to 2, right? So 2 pi by 2, now this is the way that we give polar coordinates. So 2 pi by 2 will be here, and that point will give you a horizontal tangent, right? And the other thing is, now although pi by 2 represents the angle that corresponds to this point, we can even go one complete cycle and come back here, which will give a pi by 2 plus 2 pi angle. This angle can also be used to represent the same point, but here we are not going to do such a thing, right? Because now no matter what angle we use, if it gives the same point, then we only require a single representation. So in other words, we know that cos theta equals 0 has infinitely many solutions, right? Because for all the pi, like n pi, right, now for all the integer n values, this angle, if you take it the cosine value of this angle, will give you 0, right? Will give the output to be equal to 0. So in fact, there are infinitely many theta values that satisfies this equation, but here we only consider the values in between 0 and 2 pi, that is the one within the one complete cycle. Okay, right. So now that's something you have to keep in mind. And then with all those things, we can see that at these 4 angles we have this to be equal to 0, and for the denominator at these 3 angles we have this to be equal to 0. Now here you can see that there is a common angle, right? So at this angle both numerator and the denominator will be 0. Other than that, for the remaining angles, either the numerator or the denominator will be equal to 0 individually, right? Say for example, if you choose this one, only the numerator will be equal to 0 but not the denominator, and for this one only the denominator will be equal to 0 but not the numerator, because these are the only possibilities for the numerator to be equal to 0, and these are the only possibilities for the denominator to be equal to 0, and this is the only common angle, right? Hence for these angles we have a horizontal tangent, and for these angles we have a vertical tangent, but except at this point, right? Because for this point we have to separately calculate the requirements, right? Now when you say like in the polar coordinate system, if you want to represent a certain point, we need both radius as well as the theta, but here we only find the theta values. Now therefore we have to use this equation to evaluate the corresponding theta point as well, right? So then you can see that the horizontal tangents will be at these points and a vertical tangent will be at these 2 points, but still we did not evaluate what happens in this point, right? Because at this point if you directly plug in the value, you will get 0 over 0 for the value of dy by dx, and we cannot tell anything directly by looking at this indefinite notation, right? So for that one we try to come up with a better solution through limits. So in fact what we do is we just evaluate the limit. Now remember, for the polar coordinates, in order to get the angles, what we did here is that we kept on increasing the value of angle until they reach these special coordinate points, right? So it's like if we have pi by 4 here, from the values less than pi by 4 we will be increasing the value. That means for the value of pi by 4 we will be reaching through the values which are less than that specific angle, right? So for this one also we are considering the left limit, right? Now if we just write the limit notation, that will say like it will imply the fact that we are reaching this special point in both directions, but here we are not doing so because we are only increasing the values of theta. So we are like through the values that are less than this number we are reaching this special point, right? So that's why we are marking it with a negative superscript sign to indicate that we are only considering the left end point, and we should take the dy by dx. Well, actually you have to mark it in here, okay, not in here. So it will be 3 pi by 2 negative, not in here, right? You have to mark this left and the right hand points as a superscript to this limit number. So you can compute the limit like this. Here we can rearrange the terms that we have obtained as a product of these two terms, and we can distribute the limit across these two terms, and this one can be evaluated directly by plugging in this value. And for this one we apply the L'Hopital's rule, right, to simplify this one. The derivative of this one is equal to this, the derivative of the denominator is equal to this one. Hence by evaluating this you will obtain positive infinity, right? Now how do we obtain this positive infinity? Well, 3 pi by 2 for the sine theta will anyway give negative theta, so along with this negative sign you will get positive 1 in the numerator. And for the denominator you can see we are increasing this one, this angle from 0 to 3 pi by 2, right? So just before 3 pi by 2 we are in this quadrant, right? So at this quadrant cos theta values are negative. Hence just before 3 pi by 2 we will have a very small negative number in the denominator. Therefore it will give negative infinity. Actually this should be negative infinity. Okay, so I will tell that once again. When theta is at 3 pi by 2, this will be equal to 1 because sine theta will be negative 1 and you have a negative in front, so altogether it will be equal to 1. And for the denominator, theta values will approach 0 while having, like, the way cos theta approach 0 is, now this is the 3 pi by 2 place, right? And as we are increasing theta towards 3 pi by 2, that means here we have 3 pi by 2 and we are taking from the left hand limits. That means the values which are less than 3 pi by 2. So when the theta is very close to the 3 pi by 2 but less than that value, then we have the thetas in the third quadrant, which will make the cosine theta a negative number. Remember, all sine, tan, cos, right? That's how the trigonometric functions behave. So this will be a very small but a negative number. Hence the total result will be going towards negative infinity, right? Okay, so that means suppose we have a tangent line like this and we are increasing it in this way, and then see at this point we have a negative kind of a infinity. So it anyway tells you the direction of the lines that we are moving, right? Suppose we have this sort of a arrowhead, and if we keep on moving it in this direction, then the arrowhead will be moved towards the downward direction, right? So now that means anyway we have an infinity as the answer for the derivative, hence it is a vertical tangent. So in the picture of the cardioid, if we plot all these points, now this is the cardioid, this diagram should be a symmetric one. At these points you will get a vertical tangent, and this limit equation is for the pole, right? So in the pole also you can see that there is a vertical tangent, right? And at these points you have a horizontal tangent, which you have already evaluated in the previous calculation in here, right? Okay, so that's all for this evaluating tangents.